All right. Sorry. So let's decode linear transformations, right? Now it's obvious from the title what I'm going to say the first thing, and it is that a linear transformation is just a function, right? Think of it as a function, fx, which is defined by some like what a polynomial or some function sin x cos x, anything. I mean, just giving you an idea. Okay, so linear transformation is also a function, right? Let's define one linear transformation. Say f is a linear transformation from R4 to R3, right? So what this is doing is, and let me write a function. So f R4, now the dimension. Okay, so see, what is this? This is our domain, and this is our codomain, right? Now, if like a function is 1, 1 and onto, similarly, if this linear transformation is 1, 1 and onto, that means if it is a bijection, then, okay, then this will be the range, right? Yeah, yeah, okay, yeah. Sorry, I got into thinking something. Okay, so if just as a function, if a transformation is 1, 1 and onto, that means I'll explain it later, okay, what this means. But codomain is not necessarily, like, I mean, what I'm saying is that like a function, a linear transformation can also be many one and not onto. Okay, so this property is true for a linear transformation also. All right, now let's look at a concrete example to understand it better. See, our domain is a four-dimensional vector space. So it will have four tuples, right? And it will send them to three tuples, like this. See, our input will be x, y, z, and t, right? And it will send it to three tuples. Let's, okay, I have an example with me, 2y plus 3z plus 2t. Okay, plus 3z plus 2t. Bear with me while I write all of this. 2x plus 4y plus 5t and x plus 2y. X plus 2y plus 6z plus 5t. Man, this was long. So this is what happened. Four-dimensional space transformed into three-dimensional space, right? What you can do is, okay, see, okay, what is the dimension? What are the bases of a four-dimensional space? We have 1, 0, 0, 0, then 0, 1, 0, 0, and similarly, you get the idea. 0, 0, okay, I'll write it, man. 0, 0, 1, 0, and f of 0, 0, 0. These are the bases for R4. So what this will map to is, just put the values, plug in the values of x, y, z, and t. X is 1, rest is 0, so this will be 1, this will be 2, and this will be 1. So the vector 1, 0, 0, 0, this vector in R4 is being mapped to this vector in R3, right? Similarly, plug in the values of y as 1, so we get 2. I'm plugging this value here, right? Then 4, and then x is 0, y is 1, this is 0, so I'll get 2, right? This is how I'm doing. This will be z, so 3, 7, 6, and this will be 2, 5, and 5. Okay, so this is what is happening. Vectors in R4 are being mapped to vectors in R3, right? Okay, good. So far, so good. Okay, now I should try to be okay, more structured. Anyway, see, so this is our transformation. Now I want to emphasize on something. Yeah. Okay. See, if how would we know that this is not onto? What will happen is that I should not go silent. Okay. Okay. I'll stop thinking. I'll start doing. Okay. See, now what I'm doing is I'm representing this transformation in the form of a matrix, right? So what we do is, see, we take the coefficients of x, y, z, and t. Okay, just see what I'm doing. Okay, 1, 2, 3, 2. So I'll write 1, 2, 3, 2. Then 2, 4, 7, 5, 2, 4, 7, 5, and then 1, 2, 6, 5. Okay, so this is the matrix associated with this linear transformation. What is the order of this matrix? You say it is 3 cross 4, right? Which clearly this thing corresponds to this here, that 4-dimensional space is being transformed to a 3-dimensional space. 4 dimensions to 3 dimensions, right? Also, see, now I'm transforming x, y, z, and t, right? So this is a 4 cross 1 matrix. So what do I get? If you multiply this, then you know this row into the entire column, and we end up getting x plus 2y plus 3z plus 2t, which is nothing but this. Okay, similarly, we'll get this 3 cross 1, and we'll get these 3 as the entries. Okay, so what is happening is that any vector in the 4-dimensional space is being operated on with this matrix, and we are getting a 3-dimensional vector out of it. Okay, so this is what a linear transformation is. Yeah, now let's understand the deeper nuances of this. Okay, one thing I want you to observe at this stage is, see, this is the transformation matrix I said. Now look at what we got. Okay, observe this, what I'm highlighting right now. This column and this tuple. Okay, then this column and this, then this and this. You get the idea what I'm doing? They are same. Okay, it could be possible that they give us a specific basis. Like we know that there are infinitely many bases. Any four linear independent vectors will be the basis for R4. Okay, so in case they give us some specific basis instead of these general standard bases, we will use them. Otherwise, you can clearly observe that when we this transformation matrix, if we take the transpose of it, we will get a matrix which represents the image space. Okay, R3 is the image, right? So the transpose of this transformation matrix will represent the image space when we take the standard basis. Okay, and this plays a very important role in what I'm going to do next. Okay, so yeah, let's do the next thing. Right now I'm taking the transformation matrix. Okay, let me make some space. Yeah, is there anything more I need to tell about transformations? Okay, if I will recall something, I just put it in the video. Man, I should make videos more often. Anyway, no. I make videos when I'm sure. I still am unable to structure them. Anyway, enough of blabbering. See, now this is the transformation matrix. This thing is our transformation matrix. Now what we are doing, we are going to do is we are going to find the kernel and we are going to find the image space. Kernel and the dimensions. Okay, let's just take it step by step. This is going to be a long video as usual. Okay, so yeah, let me copy this. For kernel, okay, now see what a kernel is. Kernel consists of all the vectors from our domain that map to 0. Okay, so all vectors belonging to our domain, which is R4, that map to the 0 vector, that map to 0, 0, 0 in R3. Okay, all these vectors, their set, their collection is called kernel. Okay, so understand we need to look for 4 tuples. Okay, so we will take the transformation matrix, okay, and we will reduce it to echelon form. Okay, let's do it. Yeah, so yeah, now see, if we reduce it, then negative 2 times R1 plus R2. This is my R2. Okay, you are very familiar with this now. I don't need to write 1, 2, 3, 2, but just for the sake of it, I will write it. And our R3 changes to R3 minus R1. All right. So what do you get? Negative 2, 0, -4, 0, 7 minus 6, 1, 5 minus 4, 1. Okay. And 1 minus 1, 0, 2 minus 2, 0, 6 minus 3, 3, 5 minus 2, 3. Bingo. See, these two are same. So our next step should be R3 changes to R3 minus 3 times R2, which will make this entire row 0, right? So what happened to our transformation matrix, which had vectors from the domain, right? What happened? We got two pivots. As we have discussed earlier, X and Z are the pivots, and Y and T are free variables. Okay? What does that imply? What is the rank of this matrix? The rank of F. The rank of F is 2. Okay? Yeah. Now look. Let's understand this. So rank of F is 2. Okay? That means, and what is the dimension of our domain? Dimension of R4 is 4. Okay? That means two vectors are forming the image in the image space. Okay? And like two vectors, the remaining two vectors, which is actually dimension of R4, dimension of our domain, minus the rank of the transformation matrix. Okay? Which gives us two vectors. These two are in the kernel of the transformation. Okay? These two vectors are in the kernel. That means there are two vectors which are mapping to 0. And we have done this previously also. Okay? Like, let me take this. Okay. Yeah. Anyway, see? So, we have done this earlier, and like we have done this for the solution space. Okay, what is the solution space for a homogeneous system of linear equations? We had equations, and then like we had this ax equals 0, right? So we were finding the vectors that were mapping to 0. Okay, this is the same thing. Check out the previous videos. Yeah, anyway, so our y and t are free variables here. So what we will do is to find the vectors, to find the basis of the kernel. Okay, what I'll do is, just bear with me. I will put y as 0 and t as, y as 1 and t as 0 once, and next I'll reverse this, y as 0 and t as 1. Okay, let me be more precise. See, what equation do I get from here? X plus 2y plus 3z plus 2t equals 0. Remember, we are trying to find the vectors that map to 0. That is y equal to 0, right? And our second equation is z plus t equals 0. Okay, so plug in the values. For the first vector, we have y equal to 1 and t equal to 0. When t is 0, implies z is 0. T is 0, z is 0. Now plug all these three values in this first equation. So x becomes -2, right? So this is the first vector that maps to 0. And now we put y equal to 0 and t equal to 1. Did I do some mistake? No. Okay. So I put this in z plus t equal to 0. So I get z equals -1. So z is -1. And then I put these three values in this equation. So what do I get? X is -2 into y is 0 plus 3 times z plus 2 times t is 1, right? So which is -0 minus 3 plus 2, which is 1. Okay, so these two are the basis for the kernel of f. These two are the vectors which are mapping to 0. Okay, and any linear combination of them will also map to 0, right? So they form the basis of the kernel of f, and the dimension of f is, well, clearly 2, right? Okay, now let's jump to the image, the rank. Okay, the image space. For that, okay, I'll just copy the, okay, for that, remember, fxyz was, oh my god, I'm not going to write that again. Remember, I'll copy the transformation matrix. Okay, I'll need to write that. Okay, so this was the transformation. Just let me copy it. I'll speak after that. Yeah, so these were the three vectors, and remember fx y z t was mapping to this. Yeah, just check again. Okay, so now first we formed a 3 cross 4 matrix from the coefficients. Okay, those were the vectors which were in the domain. Now we need to, you remember, just let me take you back. Okay, I could have just done this. Remember, see, we put this base vectors and we evaluated the image space, okay, which was just the transpose of the transformation matrix. So that is what I'm going to do now. I'm going to take these coefficients 1 2 1. So here it goes, 1 2 1. Remember, what I'm doing is I'm writing the vectors in the image space now, because I need to know, because I already know the rank, and the rank of the transformation matrix was 2. That means there are two linearly independent vectors in the image space. In our R3, there are two linearly independent vectors. The dimension of our range is 2. Codomain is 3-dimensional, but our range is just 2-dimensional, because two of the other vectors are mapping to 0 from the domain. Okay, I think what I said just now was a little confusing, so just ignore it. Okay, it is not of importance. what is of importance is that we have 3 dimensions in our codomain, and we have to check whether our range is same as codomain. But we already evaluated that the rank of the transformation is 2. Okay, so obviously, let's see what we get. Okay, so I'm not writing the operation, I'm just doing it and saying it. Okay, negative 2 times r1 plus, okay, I'm not changing r1, and negative 2 times r1 plus r2 is r2. So this is 0, this is 0, this is 0. Okay, negative 3 times r1 plus r3 is r3. This is 0. 7 minus 6, 1. 6 minus 3 is 3. And again, negative 2 times r1 plus r4. This is how I do. I find it easy. I just multiply it with a negative and then just add. Minus 2 plus 2, 0. Minus 4 plus 5, 1. Minus 2 plus 5, 3. Okay, so this is what I get, right? The echelon form. So let's rearrange them. 1, 2, 1. This I will replace 0, 1, 3. This is same, so I can just subtract and I'll get this. So these are the 2 linearly independent vectors in my image space. Okay. So the basis of image space is 1, 2, 1 and 0, 1, 3. Okay. So this transformation was not onto, right? Because for it to be onto, there are 2 requirements. We'll discuss it in another video, but okay, let's leave it for another video. But okay, since I've mentioned it, okay, for onto, obviously, it has to map to every element, okay, and it should be 1, 1 for it to be invertible. Okay, I'm mixing. Anyway, just remember this. Okay, also, if it was from R3 to R4, if we define another transformation from R3 to R4, this can never be onto. Okay, dimension is 3, here the dimension is 4. Okay, so this such a transformation can never be onto. The dimension of codomain should be less than the dimension of domain for it to have a chance to be onto. Okay, so I think, yeah, and also see, the nullity of the transformation is the dimension of the kernel of f, the number of vectors that are mapping to 0, which is 2. So you can observe that the rank of f plus the nullity of f actually gives us the dimension of domain. Okay, this is an important result. And let me put it in words for a better understanding. Dimension of the domain is 4. Okay, so this represents the vectors, two vectors in this particular example that were mapping to 0. Okay, and the remaining 2 vectors, they formed images in our codomain. Okay, this formed the range space, and this is the kernel space, null space, which is called null space. Sorry, not kernel space. Okay, yeah, I hope this is clear. I hope you understand what I was trying to explain. If you still have doubts, watch it again or just ask me in the comments.